Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals cosine x minus sine x. The first thing to do is find the domain. F of x equals cosine x, a trig function with no denominator. The domain will be all real numbers. Minus sine x, another trig function with no denominator. The domain will also be all real numbers. So collectively, the domain is all real numbers, or negative infinity to positive infinity. Trig functions have a tendency to have an infinite number of inflection points if they have any at all, as well as an infinite number of intervals of concave up or concave down. But nicely, cosine x as well as sine x are both 2 pi periodic, which means that they repeat themselves every 2 pi radians. Another way to write this is f of x plus 2 pi equals f of x. So instead of working on the domain of negative infinity to positive infinity, which can be a little bit overwhelming, we can instead work on the unit circle interval, which begins at 0. It includes its square bracket up to 2 pi. It does not include a round bracket because 2 pi is the same point as 0 on the unit circle. Find all results on the unit circle interval, and then we can extend those results to the entire domain by using the 2 pi periodic nature of cosine x and sine x. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F prime of x equals, the derivative of cosine is negative sine of x, minus the derivative of sine x is cosine of x. We can now find the second derivative. F double prime of x equals negative, the derivative of sine of x is cosine of x, minus the derivative of cosine of x, which is negative sine x. We have a double negative there. So we have negative cosine of x minus a negative will become positive sine x. We can now set the numerator equal to 0, and the denominator, if there is one, also equal to 0, and solve for all x's that make it true. Let's add cosine x to both sides. So sine x equals cosine x. We can now divide both sides by cosine x. Sine x over cosine x equals to a 1. The reason for this is sine over cosine is tangent. And so we have a single trig function instead of 2 separate trig functions. We need to solve tangent of x equals to positive 1. Tangent is sine over cosine. For it to be positive, we need sine and cosine to either both be positive or both be negative. For them to both be positive, that's the first quadrant. For them to both be negative, that's the third quadrant of the unit circle. To have sine over cosine equal to 1, sine and cosine have to have the same value. That occurs when they're both square root of 2 over 2. In the first quadrant, that's going to occur at pi over 4. We also need the third quadrant equivalent of pi over 4, which will be 5 pi over 4. Those are the two angles on the unit circle interval that cause the tangent of x equal to 1. Those will be the candidate numbers. We can now draw a unit circle interval line, a line representing the unit circle interval. It starts at 0. It includes its square bracket on the 0 up to 2 pi. It does not include a round bracket on the 2 pi. We can put all candidate numbers on here in order. There's a pi over 4. And a 5 pi over 4, which breaks the unit circle interval up into 3 separate intervals. We can pick a test value on each of these intervals. The first interval is 0 to pi over 4. On the unit circle, there is only one angle in there, and that will be pi pi over 6. The next interval is from pi over 4, which is in the first quadrant, up to 5 pi over 4, which is in the third quadrant. Anything in between is valid to pick. We can pick pi as a test value in there. The last interval, 5 pi over 4, which is in the third quadrant, up to 2 pi. Anything in between is valid. 3 pi over 2 will work. We can now test the concavity in each of these intervals by plugging these test values into the second derivative. We don't care about the value of the second derivative, just whether it is positive or negative. Starting with pi over 6, we have negative cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. So that'll be negative square root of 3 over 2 plus the sine of pi over 6, which is a 1/2. So negative square root of 3 over 2 plus 1 over 2. Square root of 3 is bigger than 1, and it's a negative. So negative square root of 3 plus 1 will be a negative number over the common denominator of 2. We have a negative number, a negative second derivative, which corresponds to concave down. Plug in test value of pi in. We have negative cosine of pi. Cosine of pi is a negative 1. Negative times that is a positive 1, plus the sine of pi, which is a 0. We have a positive second derivative, which corresponds to concave up. Plugging 3 pi over 2 in, the cosine of 3 pi over 2 is 0. Negative of 0 is still 0. Plus the sine of 3 pi over 2. The sine of 3 pi over 2 is a negative. We have a negative second derivative. That corresponds to concave down. So we have a concave down interval here, as well as one here. This endpoint on the right is an open or not included endpoint round bracket. The endpoint on the left is included square bracket, and that's because it repeats itself every 2 pi. And so that 0 and that 2 pi are the same point in the end. And what that means, since 0 is included, it completely closes it off, and this concave down and this concave down interval will connect together with each other. This one will exist over here to the left of it with an interval width of 5 pi over 4 to 2 pi. 5 pi over 4 to 2 pi can be written as 8 pi over 4, is an interval width of 3 pi over 4. So there's an interval of 3 pi over 4 to the left of 0 that is also concave down that will connect onto it. And that means that there is a continuous concave down interval starting from 3 pi over 4 units to the left of 0, that's negative 3 pi over 4, up to positive pi over 4. That will account for all of this as well as this connected together with each other. Then there is a concave up interval existing from pi over 4 to 5 pi over 4. Right at the candidate number of pi over 4, the concavity is changing from concave down to concave up. Therefore, x equals pi over 4 is an inflection point. It has an x-coordinate of pi over 4. It has a corresponding y-coordinate that can be found by plugging pi over 4 back into the original function. So y equals f of pi over 4, which will be cosine of pi over 4 minus sine of pi over 4. Cosine of pi over 4 is the square root of 2 over 2, minus the sine of pi over 4 is also the square root of 2 over 2. since they're the same and they're subtracting each other, it equals to 0. So it has a corresponding y-coordinate of 0. Right at the candidate number of 5 pi over 4, the concavity again is changing from concave up to concave down. Therefore, x equals 5 pi over 4 is also an inflection point. It has an x-coordinate of 5 pi over 4, and it has a y-coordinate that can be found by plugging 5 pi over 4 back into the original function. So f of 5 pi over 4, which will be the cosine of 5 pi over 4 minus the sine of 5 pi over 4. 5 pi over 4 is in the third quadrant, and it's the pi over 4 equivalent, so sine and cosine will both be negative, and they will have the same value as they would at pi over 4, so they will both be square root of 2 over 2, but negative. So negative square root of 2 over 2 minus a negative square root of 2 over 2. The double negative becomes positive. And once again, we have the same values but opposite sign combining together, so it'll equal to 0. And it has a corresponding y-coordinate of 0. This is the results over one full period. We can now use the 2 pi periodic nature of cosine x and sine x to extend this to the entire domain by adding 2 pi the period times n, an integer, to each of the x values here. Now these intervals are x intervals, so each of these numbers are x values, and we'll have a 2 pi times n added to them. For the inflection points, just the x-coordinates are x values. The y-coordinates were generated by plugging them in to the function, which is purely trig functions. So they are not x-coordinates, they are trig functions. So only the x values will have a 2 pi n added to them. That means there will be a concave down set of intervals, negative 3 pi over 4 plus the period 2 pi times an integer n, up to pi over 4 plus the period 2 pi times an integer n. There will be a concave up set of intervals from pi over 4 plus the period 2 pi times n, an integer, up to 5 pi over 4 plus 2 pi the period times n, an integer. And there are inflection points the first set are at pi over 4 plus 2 pi n. The y-coordinate does not have a 2 pi n added to it. It will remain at a 0 since it came from pure trig functions. And again at 5 pi over 4 plus 2 pi n and a y-coordinate of 0. Here, n is any integer. It can be a positive integer. It can be a negative integer. It can also be 0. N equals 0 will give the results of the original interval we worked on, and now with n being any integer, and the 2 pi period times that n integer will extend the results over the entire domain of negative infinity to positive infinity.